Back to week 10 of our robot learning reading group. My name is Steven, and Krish will be here in a second with the pizza. But today we'll be covering Pi0.6, a VLA that learns from experience. So it's a reinforcement learning paper. And before we get into the paper, I assume that some of you haven't worked as much on reinforcement learning. So I'm going to give you a quick primer on the RL topics or like concepts, and then we'll go into the paper and then discuss it. Any questions before I get started today? Okay. All right, so this first part, I think is quite important to, well, thanks to our sponsors, Palacio and Racketbot. This first part, the concepts of RL, I think are quite important to understand. So I'm gonna ask you guys to pay a bit more attention, and if you really don't understand these parts, ask me any question, I'll make it clearer for you. Because the paper builds on a lot of these sort of concepts. So first of all, what is RL about? RL is about learning from experience through trial and error, right? So the basic setup usually when we talk about RL is there's some agent interacting with the environment. And when the agent can send out different actions. So for example, if we're in a grid, if the environment is a grid, the actions could be going up, going down, going left, or going forward, back, left, and right. And then every time you step through the environment, you end up in a new state, and you get rewards for it. And through this formulation, we essentially enable our agent to learn what is an optimal policy, right? So a lot of what we talked about before in our previous robot learning reading groups have been through the concept of through the paradigm of imitation learning, where there is some expert demonstrations, which are like human demonstrations, and then we essentially learn to imitate that. But in reinforcement learning, all of this data comes from the agent itself. We don't need, as humans, to give it expert demonstrations. The agent on its own learns through trial and error what is the most optimal actions to take. And this is a very powerful paradigm that is very different from the imitation learning paradigm that we're more familiar with right now. And yeah, there's the idea of a return, which is the sum of the rewards. And return is different from reward because return is essentially let's say you're in a particular state and you take some action and you get a very high reward, but later on you get like a lot of negative rewards. So you actually want to maximize your sum of rewards over your entire rollout or trajectory, as opposed to just the instantaneous reward. Also, there's pizza. Feel free to grab some if you want. Is there any questions on these ideas so far? I don't know. You can ask Krish, I don't know. But yeah, so this is the basic setup of RL. And in code, when you use something like OpenAI's Gym, it's essentially this. For every time step, you have an environment, you can query it, send it some action that comes from your policy, or in this case, they just randomly sample from the environment, like what are some possible actions that you can take. And then at every step, you get an observation and a reward. And these are just extra info like, oh, have we terminated the episode? Or is it truncated in some extra info? And then your total reward is just summing up all your rewards. And so far, we haven't talked about, okay, how do we determine what actions to take? How do we learn what's the most optimal action? And so this I briefly talked about, right? Like what we're most familiar with is imitation learning, where we just learn the underlying data distribution, which is what the humans are doing. But in reinforcement learning, our objective is to maximize the sum of discounted rewards. So these are the two sort of opposing objectives. When we're doing imitation learning, this is what we're trying to maximize. And when we're doing RL, this is sort of what we're trying to maximize. So the rewards come from, again, the interactions with the environment, whereas when we're doing imitation learning, we just have some data set. There's no concept of rewards. And when we're doing imitation learning, we just have some ground truth labels, which is the actions that we want to take in the context of robotics. And the reason I'm juxtaposing these together is because, as we'll see in the Pi0.6 paper, we're trying to unify essentially some of the advantages of this and some of the advantages of imitation learning and some of the advantages of reinforcement learning. So in particular, what are these advantages? By the way, yeah, this is just a slide to show that with RL, we've been able to solve a lot of very cool, very hard problems. So AlphaGo, Atari, and then this is a Unity robot that learned to dance. And this is a Rubik's Cube being solved through RL. So all of these are solved using RL. There are different instantiations of the specific algorithm used, but fundamentally at the end of the day, all of these, the way these learn was through trial and error. There's some exception here, like this is trained with mocap data, and then you sort of, the rewards is the tracking of your motion capture. But you can just think of it as all of these are environments that provide you with some reward, and people figured out how to create an algorithm that can maximize the sum of discounted rewards or the maximize the return. And we end up with these super capable algorithms or these super capable policies that can solve a Rubik's Cube, that can solve AlphaGo, that can solve Atari. But what you will notice, right, AlphaGo, it was just trained from its, well, AlphaGo was trained a bit with, I think, expert demonstrations, but AlphaZero was trained purely from self-play. This, Atari, was also solved just purely from the agent interacting with the environment, right? But the limitation of these things is that they're very, very sample inefficient. Do I talk about it here? No. OK. They're very, very sample inefficient. And I want you to keep that in mind. So with imitation learning, right, like if you think about how ChatGPT or these LLMs are trained, we essentially have like a huge corpus of text, right? And then we're trying to essentially do this cross-entry loss or like imitation learning on this expert demonstration, which is the internet, and it's very easily scalable. Whereas if you look at RL, right, every time step, we're interacting with the environment. And this can be very dangerous if it's like a robot, imagine like a self-driving car in the real world, and you're trying to do RL. It can be very dangerous, and it's also very slow and very expensive, right? So like you can imagine if I'm trying to do RL with like folding a t-shirt, and you're doing this online, takes a lot of time, right? Which is why a lot of these are trained in simulation. Even the Rubik's Cube, that one was trained in simulation, and then you do different tricks like domain randomization to make the simulation environment more difficult than the real world, and then you end up being able to solve it. But for like t-shirt folding or a lot of these current robot learning tasks, it's quite difficult to make it work in simulation. OK. Then there are the families of RL algorithms. I think what is particularly important that I want to point out is the difference between value-based methods and policy gradient methods, right? Because I think a lot of you, when you think RL, you just think like PPO, which is over here. But while in the Pi0.6 paper, they kind of used, they had an ablation with the PPO, most of the ideas are just purely from this section, which is value-based learning. And to explain to you what value-based learning is about, we're going to go to the next slide, which is what is value-based RL about? Right. So again, our idea in RL is what? What's the objective in RL? Can someone tell me what the objective is? To maximize? Maximize reward, or maximize return, maximize sum of rewards, right? So that is our objective. So what we're going to do in value-based RL is first, we're going to learn a function that captures what is the return. So that is our value function, this Q. And so we're going to first learn a function Q that tells us, OK, I'm at this state. How much total reward do I expect to obtain? And once we have that Q function, what we can do, if it's a value state function, or a state action value function, which means you can pass it a state and an action, and it will tell you a value. Once you have this Q function, what you can do, assuming that your actions are discrete, so you only have like five different possible actions, like going forward, going back, going left, going right, then you can just look, I'm at this current state. If I look at, I have 5 different actions, and I just look at the 5 different Q values, which one is the highest value? And then you can just greedily take the one with the highest value as your optimal action. That is the idea of value-based learning. And so the algorithm sort of works like this iterative fashion where first you do policy evaluation, which is you learn a Q function that captures, okay, I have a fixed policy. I'm trying to evaluate how much reward do I expect to gain by following this policy. And then in the improvement step, we take a max of the action so that we sort of greedily the Q can only get better. And so this is actually also called a Bellman optimality update. And this is sort of the equation behind Q learning. That's a lot if maybe you haven't worked with Q learning as much before. So I guess what I want you to take away from this is that in value-based learning, we first learn a value function, and then we'll use this value function to train our policy, to update our policy, as opposed to directly optimizing our policy, which is what happens in the other camp of if you were to go in these policy optimization camps. Did that make sense so far? I know it's a lot, and you might be wondering, like, why am I talking about all of this when it comes to RL? Yeah.
Can you only use the Q value function in practice, or can you use it in simulation as well?
Can you? Are you only allowed? Why would you only be allowed to use it in sim and not in the real world?
No. I guess my question was the opposite. But can you use it both? Like, can you only use it in sim? Or can you use it in sim at all?
So in the real world, yeah, you can use in the real world, generally, like let's say for robot learning, what you would do is the Q function, you'd use like a deep Q learning algorithm. If it depends on the setup, right? So I'm going to talk about it in a second. Like in the real world, if your state are images, you need to encode it, and then let's just assume that you have discrete action space and continuous state space, because Q learning is mostly for discrete state space, right? It doesn't really work well with continuous action spaces. So let's say it's continuous state space. You can literally run. Do I have a slide on deep Q learning? You just run the deep Q learning algorithm. In practice, so in the paper, what they'll do is they'll do some form of value learning, and then it's not exactly Q learning. They'll just do like multicolor learning, and they'll just use the sum of returns as a target, and then they'll use the Q function, and then they'll figure out how to extract the Q function into a policy, or the value function. They don't use a Q in their case. So yeah, but your question makes me, brings us to a point of when in this paper, Pi0.6 paper, or like any sort of paper that uses the idea of value-based learning, you then later need to figure out, because you're only learning a value function, if you work in a continuous action space, you need to figure out, okay, I have a value function. How do I determine a policy, right? So if the actions are fixed, you can always take the argmax. But if the action space is continuous, it's not so clear, because you can't just try every single action, or like, does anyone understand what I mean by continuous or discrete in this case? Yeah, right. So like, if discrete would be there's like only a given set of things you can do, going up, going down, going left, going right. Continuous would mean instead of just saying going up, going down, going left, going right, it's a continuous number, right? So let's say you're steering, right? So if you're steering, if it were discrete, you could say left or right. But continuous would be I output some number, some steering angle between -90 and 90. And you can see how there's an infinite number of different actions to pick, right? You can pick 89.9, you can pick 89.995, etc. So continuous action spaces are much harder to work with. And so when people solve Atari, for example, this was DQN. The action space here is actually discrete, so it's actually a bit easier. Even though the state space is continuous because it's an actual image, the action space is quite straightforward. And so this was solved like in 2017 or 2015. Okay. And there's Bellman equations, there's Q learning. But I think what I want to get to is this, like, combining the benefits of data with real-world experience, right? So this is essentially what Pi0.6 is trying to do, and actually, I guess a lot of the research currently, and part of the questions that I'm also interested in, right? Reinforcement learning does not make use of real-world data, but it learns sort of an emergent behavior from the rewards. We don't explicitly tell it what to do. It will just learn on its own what are the best behaviors or best actions to take to maximize the return. And on the other hand, you have like data-driven AI, right? Like we explicitly show it what it needs to do, and it just learns to imitate us. But data-driven AI is also very powerful because it can, like, for example, generate images, right, that are really, really realistic. And then for us, for robot learning people, we have these like really impressive models that can do all sorts of different tasks. And so how do we unify this? We unify this through this idea of like doing offline RL. And so offline RL is this idea that instead of, by online I mean in real time, you have a policy, you step one time step to the environment, and then you update your policy, and then you step once and then update, step once, update. Instead of doing this online, what you're going to do is store, you have like some sort of data set or some offline buffer that you're learning from, right? So in the context of like robotics, what would be the offline data set? It would be like some expert demonstrations. But you would also have the rewards baked in. So in our case, if we want to adapt a robotics data set for offline RL, you just need to add some sort of reward signal. It could be like a sparse reward signal. So if like the t-shirt was folded at the end, you give it like a positive signal. Or if it was like a bad fold, you give it a negative signal. That's the only thing you need to add. And then like you somehow figure out, in addition to, so here you would just learn how to imitate this data set, in imitation learning, you only learn to imitate the data set. Here, what we can learn is, in addition to how to behave, you also learn the value function, right? And the value function will tell you whether it's an optimal, it will teach you how good a particular action is, right? So if I take 2 minutes to stack, some plates, and there's another demonstration where I only take 30 seconds to stack a plate, ideally, we can learn that the one that takes a shorter amount of time is better, right? But if you were to only do like imitation learning, you should have half the time you copy like a 30-second demonstration and half the time you copy a 2-minute demonstration. So in practice, ideally, this is really what we want. We want to take a data set, learn how good or bad it is, and then afterwards, we can do online fine-tuning, right? So as I said, this is very expensive, very dangerous, and before we would always train this from scratch. But if we can somehow augment it with pre-training data and then do online fine-tuning, then that would be really powerful. And so in Pi0.6, that's essentially the sort of paradigm that they're going for. And does all of this make sense so far? How does online or offline RL work and how this fine-tuning process works?
So what was the difference again? The offline to basically have the world model in the buffer, right?
It's not exactly a world model. It is just a set of transitions from one state to the other state. And you learn from a fixed data set as opposed to learning on the fly as you interact with the environment.
So it's like my stockfish AI. I use a stockfish data set to regress, how valuable the state is board instead of training it a billion times with AI for AI.
Yeah, that's a right way to think about it.
Actually doing that in chess.
Yeah.
Unknowingly.
Nice.
Waterloo is the thing that was done for language models like ChatGPT and other models.
Yeah.
Where they first pre-train their transformer to predict the next word, and then you can see sometimes when we're sending messages to ChatGPT, they're asking, okay, do you prefer this response or this response? And they use that to do reinforcement learning to create their answer.
Yeah.
I think it's considered as offline reinforcement learning.
I think the analogy there is not perfect, although I did put RLHF as part of some of the RL stuff, or ways we solve RL. the reason I don't think it's a perfect analogy is like when you do RLHF, it's like, yeah, you do pre-training and then you do fine-tuning, and then the way you do fine-tuning is to RL, right? But here, what we're doing is like, even in our pre-training, we want to learn like the structure of a data to like figure out what is more optimal, what is less optimal. Like when you train an LLM, it's literally just cross-entropy loss. You don't know, like you don't still discriminate good data from bad data. It's more like in the RLHF phase, in RLHF, what you do is you label some of your preferences, then there's a reward model that's learned, and then your thing needs to learn to maximize the reward model, but then you also need to be careful that it doesn't run for too long, else it overfits the reward model.
I think it's also because it's really hard to say like this answer is better than this answer. Like it's really hard to like evaluate how good is the answer.
You're saying it's really, really hard to give reward labels for language models, which is why it doesn't exist. Yeah. Yeah. I think, yeah, in general, RL, one of the reasons it's really hard is this idea of, it all relies on rewards, right? And so how do you get rewards in simulation? If the objective is very clear, like games, which is why games have been solved so easily, right? The reward is very clear. It's like at the end of the game, who wins, who doesn't win. But like, even if you think about our everyday tasks, you know, like doing laundry, there's like different qualities of the final thing, right? Like, what do you define as finished? If you fold a t-shirt, like there's different levels to it, like how well it's folded. And so data quality, like the quality of the folds should, in practice, be accounted for. And then it's a lot of like human labor if you do it in the real world to explicitly label the rewards, right? You need some way to compute the rewards. Yeah, I don't want to take up too much time on this RL part because I want to get to the paper. I have some slide here on explaining why offline RL is hard. And I don't know, are you guys interested in why offline RL is hard? Because,
yeah.
Is everyone following? Okay, why offline RL is hard? So remember, in online RL, right, what we're doing is, okay, let's assume we're doing value-based RL. We're learning a Q function. Initially, our Q function is randomly initialized, right? We don't know what the values are. So what we're going to do is apply this Bellman update, or we're going to do what I talked about. We do policy evaluation and policy improvements. And so you slowly update your Q values through this equation. But what happens in offline RL is that your data set, your transitions from old state to new state is fixed, and so is your reward, right? So what can happen here is you start overestimating your Q values, because this tells us that the value of the current state is equal to the reward we get from this state plus the best, if we take the best action at the next state, what is the highest value that we get. But the issue is this A prime here, right? This can be any different action. In the offline setting, we can't actually go and try this A value, right? Because you can imagine if you do online RL, you have this QSA, okay? And then let's say you estimate for some particular action, it's like really, really good. And then by sheer luck that you get really good, right? Because initially QSA is all randomly initialized. But then, okay, if you think it's really, really good, the next time you end up in this state, you're going to visit that state, and you're like, wait, this state is actually not that good. So it actually compensates itself. But in offline RL, because your data set is fixed, you can't adjust for this behavior. You just start estimating its much higher value, and you sort of end up with this graph of this is how well it actually does, and this is how well it thinks it does. So it overestimates Q values. Yeah.
How is offline RL logically different from data-driven?
How is it logically different from data-driven, like imitation learning? Logically, if you look at actually, I guess it depends on how you do. Logically in offline RL, currently how it's done is you do it in 2 steps. You train a value function. I don't even know if it's analogous because there's no actions or I guess you can see if the.
Can't you equate that to a imitation learning approach? Mathematically.
Yeah, mathematically, I could equate like, I can equate just like policy gradient with, I can equate like policy gradient with just pure your cross entropy loss. But I don't know if that's your question. Can you rephrase your question, or like can you repeat it so I can try to better answer it?
So, like, I don't know too much about offline RL, so I was wondering how you have kind of like this fixed data set where you can't really explore. So, the benefit of RL over imitation learning is you have that state space where you can actually explore different actions. So it kind of learns on its own, right? That's how it can actually get better the data that is presented.
That's right.
But in offline RL, if you don't have that search space, how is that any different from imitation learning?
Because
It's kind of like a different sort of architecture.
yeah, I guess you can think of imitation learning. You're purely learning a policy, right? And you're just treating everything in the data set as like ground truth, and you're trying to match its data distribution, right? But if you were to do alpha and RL, even though you can't step to the environment, you're going to try to learn like you still see reward, right? That's the extra thing you see in RL. And so what you can do is like you can maybe first learn your value function and be like, okay, some of these actions are worse, and some of these actions are better because when you take those actions, you get lower reward. Okay, then your policy, when you train your policy in offline RL, you can use your value function to make a better, you can weigh it. So the simplest formulation of offline RL is advantage weighted regression. It's kind of like this, where maybe I had a slide at the very, very end for this, but it's essentially called like policy extraction. And right, so this would be, for example, offline RL. You have SA from a data set. You have these value functions, okay, that you train from the same offline RL data set. These will tell you, this will accept QSA minus V of S will tell you the advantage. So it's like how much better is this action compared to some other action. And then you just weigh your log likelihood by this number. So what in practice will do is the actions that you think are higher will give you higher value will be weighted more. So the policy learns to imitate these actions more than some other actions. Whereas if you didn't do, if you just got rid of this, this would just be your imitation learning loss or like data driven.
Okay. I was just wondering if it's kind of like the value function and the policy function. If they're like one and the same thing in this case, but like I'm not sure, because like what's like I'm
they're different.
Mathematically condensed.
If it can be mathematically condensed, then you would be policy gradient.
Okay.
So if you do policy gradient methods, you can actually plug the so in policy gradient. So this is like the most simplest form of policy gradient, right? Your goal is to maximize the reward, and you can plug in. You know what reward you get because you know your policy. Its probabilities, right? So the rewards you get is just if you step through, if you use your policy, you start at some state. That's your tau is a trajectory. You have like some probability of getting into some state given action. So this sort of represents a rollout, and then you get some reward at the end, and you just weigh the policy term by the reward. So the ones that with higher rewards, you'll weigh them more for this. And then you don't need to explicitly learn a value function because you just directly use the reward. The issue with this is that when you do the learning, the data that you learn from always needs to come from that policy. So what happens when you do these methods, policy gradient methods, is in practice you'll collect data, update your policy, discard all of your data, get a new data set, and then update your policy, and then discard the data set. And so this is on policy learning. And if you compare that to value-based learning, you can have a bunch of demonstrations from different policies, right? Because we're learning from, let's say, human demonstrations. You learn a value function that works for any demonstration, and then you can leverage that to train a policy. Yeah.
I guess the follow-up question would be: so in offline RL, that reward is not technical. So in online, like regular RL, the reward would be kind of deterministic of like what the agent sort of does, which is initially random, right? But in offline RL, that reward has already been set in the data set. If that makes sense. So, like, how is that really a reward function? Is that kind of part of the data? Does that kind of make sense? As in, like, how does the person, like, isn't the reward function dependent on the person who made the data set? So it's kind of like imitation. But like I might be.
I guess you can imagine like, you just run a random policy in the environment, and then you just store it, and then you just like, okay, that's your data set, and then you try to learn from it. Then it's more like the formulations, like instead of doing it after every step that you step to the environment, you're just like, here's a data set, try to learn a policy. You're not allowed to interact with the environment. Just try to learn whatever you see. Like, okay, what do you think is optimal from like these demonstrations, and what do you think is not suboptimal? You don't get the chance to use your policy to step to the environment. Yeah, but you learn a value function.
So it's just a value function.
You learn a value function, and you learn there are different ways to extract it into a policy. Right? Because like in imitation learning, you would just learn the policy, and that tries to match the data distribution of the data set, which only cares about state action, and doesn't even care about the new state you end up in, and doesn't care about the reward. But in offline RL, you try to leverage all of the information, the rewards, the new state, and yeah, the full transition.
In the case of like Pi0.6 though, it's like the value function that we're learning basically equalized, because you have all the data you need, and you've basically decided what the reward should look like, and then you're basically training value function to predict the rewards.
Yeah. So in Pi0.6, what happens is you have episodes, right? And each episode has a bunch of rewards, and your value function will learn, given the 3 images, how much reward do you expect to get, and the reward they use is -1, -1, -1 until the end, and then I think it's 0. Yeah, if it's 0 if it's a good demonstration, and maybe we can.
Like the probability distribution, right?
Yeah, you mean like the use bins?
Yeah.
Yeah, that's more of an implementation detail that I thought was interesting. But okay, we're jumping a bit ahead. I was trying to answer your question on what they actually do in Pi0.6. Maybe we'll get to this one, and then we'll go over this in a second. Any other questions on this? I was really trying to give you guys context on where we come from in reinforcement learning, and so I had this final slide of like right now we're in the era of like, how do we apply RL for VLAs? And I was trying to walk you guys through where did we come from? We came from Q learning, deep Q learning, and I guess I didn't talk about this, but traditionally these RL methods, they use very simple Gaussian policies in the case of continuous action space, which means, let's say I want, like the number it predicts follows some Gaussian, and then what you do is like, you'd sample from this Gaussian, you can either sample from it, or you could just like take the mean of this at test time. But it's not very good at capturing multimodal distributions. So, do I have an image? All right, like, I think I had an image somewhere of, maybe I don't, flow matching somewhere? Okay, maybe it disappeared. The image I'm thinking about is like, let's say it's like the push T tasks that I showed like in week 1 or week 2 of the robot learning group. And if you're trying to learn, there's like sort of 2 unique distributions. So there's 2 modes. You can't really do that with Gaussians because they're unimodal. You could kind of do like mixture of Gaussians, or mixture of Gaussians where there's like 2 Gaussians together. But right now the paradigm is diffusion and flow matching. And so getting it to work for these kind of policies, more expressive policies, is really, really hard, because when I was going to, if you look at this slide and how we derive the policy gradient method, right? We can, for Gaussian, the log probability is given by this, and we directly optimize the log probability. And in the case of these more expressive flow matching or Gaussian probabilities, you can't directly compute the probability of an action given a state, because you're doing this like iterative process of like you're starting from noise and you're adding it. Like it's not tractable to compute this probability. And so because of that, these methods sort of fall apart. And so what happens is you just need to first learn a value function, and then you figure out like, okay, there's some information I know from my value function. How do I distill it down into my policy? And that process is called policy extraction. So back to your point of like, how is it different from imitation learning, right? Like imitation learning, you just have this policy, but in offline RL, currently the paradigm is, yeah, you learn some value function, and then you try to figure out how to distill it down to your policy. And the idea being like, you can maybe make your base imitation policy way better because you know what is optimal and what is suboptimal. Huh?
Kind of like fine-tuning.
Yeah, kind of like fine-tuning. And yeah, so like you do offline RL and then you do some online RL fine-tuning.
We do have a few immersion studies with SAP.
Yeah. I found this paper, Flow Matching Policy Gradients, because I was saying, oh, policy gradient doesn't really work on non-Gaussian policies because it's not tractable, but it turns out maybe it is. Like this came out like 3 months ago, and they mentioned this in the Pi paper, and they figured out how to do PPO for like these super complicated flow matching policies. And I didn't have a chance to look at the paper, but if you're interested, take a look, because I will take a look probably eventually. But yeah, this okay, what time is it? 7:45. Sorry, I went a bit longer for the RL part. Modern age RL for VLAs is we don't know how to directly optimize a complicated policy for RL, so we break it down into 2 parts: learn a value function, and then learn how to extract the policy from the value function. And yeah, now I really want to go into the Pi0.6 paper. Really apologize, I went a bit longer for the RL section. Is there any questions on whatever came before in terms of RL context? Because this sets us nicely for what the Pi0.6 paper is about.
What would you say the trade-offs are between using like a model-free approach
And model-based?
policy gradients?
Did you say model-free versus model-based?
Yeah, exactly.
Well, model-based is if you have a perfect model of your environment, then in theory what you could do is just use your model, right? As opposed to doing it in the real world. Like you can basically do things for free, basically, right? Like let's say you're training a self-driving car RL policy. If you already have a model of the world, you can just try it in your own internal world model, and then you don't need to do any of these model-free approaches. It's much more efficient with model-based because you understand the dynamics, you know, what the rewards are going to be. But the model might be it's going to be a model. It's going to be a simplification of the real world. It might not be perfect, so it might be more sample efficient, but it might also be incorrect. It is a very active field of research, so I do think it's quite promising, especially for like if you look at like training robot foundation models. If you can leverage a world model, then you can have your policy learn in its own world model, right? But the world model needs to give it like accurate future states, right? If it's like inaccurate future states, then it doesn't really work. Like the problem I'm thinking about where world models could be really useful is especially like if you look at when a robot fails, right? And it does some tasks and it fails because it's out of distribution. In theory, if you query it to the world model and it retries in its own internal world model, it can kind of figure out like what is the set of actions it can take to end up in a good state. But if like your world model also ends up being out of distribution, then like it's sort of like a circular problem where, yeah, you just need a really good world model. So it also adds more complexity. But yeah, I don't have a perfect answer for you. I guess this is my best answer so far.
Yeah, that's
Okay, so Pi0.6, high level what we're doing is this offline RL, or we do this batched RL thing. This actually came from another paper that I was reading a few months ago, right? But the basic idea is you have some base policy, you have a value function, and what you're going to do is, because we're running this in the real world now, okay? You can't just like do m.step once and then update your policy and then update your value function. That's going to be way too slow. So what happens is we collect things in batches, and then we take that data set, right? So we collect some data, add it to our data set, and then we can retrain a value function, and then we do policy extraction to figure out how to update our policy based on our value function. And then hopefully this new policy should be better than the previous policy. And then you sort of repeat this process as many times as you need to. And so this is what they talk about in the paper: collect data, train a value function, and then this is the policy extraction part. Does this make sense? Any questions? Yeah.
When you return your value function, what do you do with your old one? Like, do you like
discard it or yeah? That's like engineering. It's more of an engineering thing. Like in practice, what people do is it will be kind of like a sliding window. What happens is like if you discard all of your data and then you only like use your new data to train your value function, there's going to be a huge like distribution shift. So your value function will be like, oh crap, like this is all new data and it's going to go crazy. Yeah. So in practice, you want a kind of a smooth sliding window, and you might set like a maximum buffer size.
Buffer size.
Yeah.
Okay, so it's like, okay, that makes sense.
Yeah. Any other questions? Okay, so how did they train the value function? It's actually quite straightforward. The target that they're training on is RTB of tau, which sounds scary, but it's essentially just the reward. So you look at your where you're currently at, and you look at your remaining rewards, and you can sum them up, and then that gives you some value. And what's interesting in this paper that they did that's very different, that I haven't really seen before, is that they actually discretize this value, the sum of rewards, because usually the sum of rewards is some continuous value, right? It can be any reward, but they discretize this value to 201 bins. And I think the reason they do this is just because of, I guess, what in language modeling we use tokens, and I think it's likely that it's much easier to learn when it's discrete as opposed to continuous, right? Because you can imagine you have only 201 targets as opposed to some continuous value from, it could be any value essentially, right? And so I think this just makes the learning problem a lot easier, which is why they did it. And the second thing that I think is very interesting is that they use Monte Carlo targets. Yeah, question?
So the one number related to like, because we're using pre-trained VLM. Mm-hmm. I know that the output of this VLM, there is like some free tokens that we can use to map our like talks or actions. And so is 201 not related to the number of free tokens that are available at the end of the pre-trained VLM?
Yeah, I don't think it's related in this case. I think this is literally like you can have like a feed-forward network with like 201 output layers. The final layer is 201 neurons, and then these are all logits, and then you just do a cross entropy loss, and that's how you get that number. Yeah.
Do you know how they chose 201?
Yeah, that's a good question. I actually did not have the time to look into why 201. But yeah, it's definitely like weird, right? Like 201 is very weird. The other thing that they did is Monte Carlo returns. Okay, this is more of a minor details, but I think this is like a lot of times when we do RL, we do something called like a Bellman update. So instead of like taking the entire reward until the end of the episode, we will take the current reward plus an estimate of the next reward. So we bootstrap as opposed to do a full Monte Carlo rollout. But in this case, they don't really bootstrap. They just like use this as the true regression target, which I think makes sense because when you bootstrap, it's a very biased, it's a very biased but low variance target. Whereas when you do this, it's a very high variance but low bias, or there's no bias when you do this. So it's, yeah, go ahead.
I don't know if you know, can you explain Monte Carlo returns? As opposed to
yeah. Let me go to my notes then. And step Monte Carlo return. Do I have a good visual for this? I mean, the idea is very simple, so maybe I don't have a good visual, but Monte Carlo, or maybe I have n-step return. N-step. Okay, maybe I don't have n-step return as well. Maybe let me Google this. N-step. Yeah, I guess the difference is so you can go between TD and Monte Carlo, and an n-step return is somewhere in the middle. So what happens is when you train your Q function and you want to learn a Q function, right? You're at a given state, and then there's a bunch of more states you need to visit and rewards along the way until the very end, right? And so if you want to learn what is the value function at this current state, what you can do is you can be like, okay, this should be the sum of all the different rewards until the very end. And that will be a Monte Carlo return. So to update the Q function right now, I need to finish completing an entire episode. And then I'll be like, okay, now that I know what my actual return is, I'm going to update my current value here based on everything there. But that's obviously very slow because you need to like do a full episode until the very end, until you terminate, before you can update your Q or your V. Now, on the other hand, you have one-step or TD backups. What that will do is you already have some Q function. So why don't we just use that Q function? So what I'll do is like the reward here, the Q function here should be equal to the reward that I get from in my next state plus whatever the Q function is there. So you can break it down into two pieces. It's kind of like doing dynamic programming. And this works. There's like theories on why it works, but I also tried implementing this in practice. Like, it ends up converging a lot faster when you do like the TD backups, because you can just update much more frequently your Q function, as opposed to like you finish one episode and you only can update this once, as opposed to like you can update all these values together as you move. So does that answer your question?
Yeah.
Okay. Okay, so they train the value function, and at the end of this training, what you get is you're given some state, and we know how good this state is, right? And so if it's like, I think today they tried it on laundry folding. If the t-shirt is like very crumpled, it will have a very negative value function, but if it's close to finishing, it will be much more positive because you're closer to a success. And yeah, I think like in practice there's some tricks of like -1 and zeros as opposed to 0 and 1s. Though this is kind of industry standard. Yeah, the main thing for me is that we're interesting is Monte Carlo returns as opposed to bootstrapping and using discrete tokens. I thought were very interesting ideas. Oh, the deep Q learning stuff is here. Okay. Yeah, I was trying to show this, which is like, Chris, you're asking like, what was your question? Your question was, can you use Q learning in the real world? Like, I wanted to do an analogy with deep Q learning, because in deep Q learning, yes, what they do is this bootstrapping. So you have your target is given by R plus the max of your Q at the next state, right? As opposed to doing a Monte Carlo, you do a TD, you have a TD target. And then you regress with regard to your TD target, not the full rollout. So this is like more standard. But so what they did here is the full Monte Carlo rollout, which is why I thought it was quite interesting. And then yeah, so what you get is, again, this is a diagram showing the Q function over time. And as you get closer and closer to finishing, the Q function goes up, right? Yeah.
Is this a Q function?
Oh, sorry, a V function. I keep saying Q, but it's a value function. Yeah, I guess like why they chose a V as opposed to Q is also interesting. Like a Q function, if you're working with like continuous action spaces, because like they're just like inputs to the model, right? So like it's just an extra dimension for the action, or however many dimensions your action is. And so the Q function, I mean, the value function under the hood is just a big transformer with a value head. So there's no reason why instead of a V of S, you can do V of SA. You would just have like an extra input here, which is A, right? I guess maybe.
I think that after at least when I read it, it seems
Yeah.
like, well, they just want the advantage if you can just get that with the value.
Yeah, that's true. But the advantage is like many formulations of the advantage. Yeah, theirs is like R plus V of next state minus V of S. You could also do like Q of SA minus V of S. But yeah.
That would require both.
A Q and a V, yeah. Yeah. Yeah, there's different formulations for this, depending on how you want to set it up. Okay, I think the interesting part is the policy extraction. We have a value function. How do we get a policy. And what I wanted to say here is, I think they talked about regularized reinforcement learning, which is sort of like a slight variant of regular RL, where instead of the objective being purely maximizing return, you add a regularization term. And the idea of why you would want this is, I sort of intuited it through this diagram. Right? You have like catastrophic forgetting if your like policy deviates too much from your original policy, it might be like much worse. So there is like something good perhaps in keeping your original policy or like the new policy closer to your reference policy, and so you want to regularize it to an extra term. And they use this idea when it comes to training the loss. And in their loss, they're going to have essentially both the conditional policy and the unconditional policy. Okay, what does that mean? So you'll see that between these two pi's, the only difference is one of them is conditioned on I of t. And I of t is just an indicator variable that will say if this action is good or not. And the way you know if it's good or not is if you look at your advantage function, if the advantage, which is you take a reward with your next state minus your current state, the value at your current state, if it's greater than some threshold that we've set, then we set it to 1, right? And I was looking more in the paper of like how this is implemented is literally just a text token, like advantage positive and advantage negative. So you sort of use your value function that you trained, and then if you see that, oh, this action, we think it's a good action, we're going to tell our policy that it's a positive advantage. And they sort of train this, and it sort of learns to maximize both the unconditional policy and the conditional policy's lock likelihood. And in practice, what happens is at test time, you ask it to generate good actions. So from what I understand, at test time, you will always say like advantage positive. And the policy will only output actions that are positive, like that are positively labeled. And the reason it works is at training time, okay, we figured out which actions are good. So the loss is going to be of the conditional policy. The action that we'll see is only those that are good. And at test time, you only query this one, and you basically only generate good actions. And yes, at test time, you have your value function, you run this. Or actually, you don't even need to run this at test time. You just give it this extra token, advantage positive. And that's how you get your test time improvements. And yeah, this is the full picture of the value function with the policy. Yeah.
Yeah, this is something I didn't really understand.
Yeah.
So during test time, yeah, they set the advantage to true.
Yeah.
Which means that if you set the advantage to false, it will give you bad actions.
I think so.
The model is wasting parameters remembering bad actions.
I think actually it might only, like, it only is trained when I of t is equal to 1. And so when I of t is equal to 0, it doesn't use it or somehow like, because it's a Dirac delta function or something like that. It wasn't 100% clear to me as well, yeah. That is, yeah, it is slightly confusing. But why would it be a bad issue? Well, like, you're saying it's wasting computation on learning bad actions.
It's wasting computation knowing how to generate bad actions.
But maybe it's a good thing to know how to generate bad actions.
That could be the case.
Yeah.
I don't know, I'm not sure either.
But yeah, I think that's basically the policy extraction part. And so if you combine all of this together, this is essentially the batch online RL loop that I showed you guys, but they have some extra steps of 4 to train the value function on both the demonstration and autonomous rollouts. Yeah, they probably should have like condensed down this pseudocode. And the evals, I think, is the last thing I want to touch upon, and then I'm really going over time. The evals talk about different setups of what works and what doesn't work. So the pre-training is basically if you only do imitation learning, right? And if you look at if you do offline RL, and there's like a few versions of their offline RL, right? So if it's just offline RL with pre-training, which means I think you train your value function. If you just do RL pre-trained, it's actually not super, it's better, but it's not super duper good. If you do offline RL with SFT, which is trained by fine-tuning the base with demonstration data, and there's, okay, I need to double check the paper for the differences, sorry. Let's go over here. But I think my point with this was like, it's still very, very hard to get offline RL to, or getting RL to work in general with your VLAs. And so you need to be very careful about how you do this. So this is the final model trained with recap, including both autonomous rollouts and expert corrections. I see. So does this mean, I think this doesn't leverage the autonomous rollouts. It only uses expert data. And then this is fine-tuning with demonstration data. And then I guess, theirs is actually, if you include autonomous rollouts with both the expert demonstrations, then you get a lot better results. Yeah.
For the reward mapping, they annotate every
Yeah, it's well, not every time step because they're using sparse rewards, but the way they, how do you, if you want a robot in the real world, right, and it does a task, how do you know if it's finished, right? And in simulation, you might have some logic to check for it. And maybe you could do the same in the real world. You could check if the table is empty, then you can assume it's clear. But from what I saw in the paper, they manually did this at the end, I think. Annotator. Or experiments.
So they annotate a lot of random frames, not random.
Yeah, but I think they already kind of do this because there's subtask labels within a particular episode. So there's already some extra manual annotation with the data. Let me just double check where the experiment says. Because I did remember they said this in their limitations. First, their system's not fully autonomous. It relies on human labeling and effort for reward feedback and episode resets. So there are ways to automate this, but it seems like they did not do it in this paper. Yeah. But yeah, I think that's overall what I wanted to cover today for RL. I apologize, maybe I went too long for the reinforcement learning section and I might have lost one or two or a few of you, but I hope this gets you guys excited about RL, right? Fundamental idea, we figured out a way to let our policies learn from their own demonstrations. Previously, this was not really possible, or if you did it, it would actually do worse, right? Because if you have a policy just learn from its own rollouts, there's a huge distribution shift. And figuring out a way to do it such that the policy improves is non-trivial. And so they figured this out. But there's still room to improve. If you look at their results, we're still only about, say, what's their success rate here? I mean, yeah, some of these laundry failure modes, actually that's the throughput. 80%. Yeah, we're getting closer to our 100%, but I guess the throughput can still be better. We're at, I guess, 1 t-shirt a minute right now, which is not bad. But this is, running, I don't know how long they ran this for. They might have ran it for 24 hours. Yeah. Okay, any final questions? Yeah.
Are you gonna try this? Because I remember you were trying to
Yeah, getting RL to work. It's on the bucket list. I think currently I want my just purely VLA to at least be semi-robust. Like the thing with these RL things is like they're really hard to get working right. I'm sure like they spend a lot of time tuning stuff, whereas like I can just scale data collection a bit more. I thought I would solve it with like 200 demonstrations, but it seems to not be enough.
For what? Supervised?
For just fine tuning, yeah, for fine tuning with like 200.
Yes.
Yeah, but maybe it's because it's a VLA, and maybe I can just use like something simpler because I don't really need language conditioning right now. So, yeah. Okay. Any other questions? Okay. Well, thank you guys for coming, and does Krish? Oh, is Krish not here? The other Krish. Okay. Do we? Yeah.
Please post the slides on the Discord.
Okay. Yeah, I can post these.